In a separate video, I've talked about the fact that energy equals Planck's constant times frequency. But usually when we're talking about light, especially visible light, things that we're seeing every day, we're usually going to be referring to wavelength. So how are we going to be able to convert from wavelength into energy? We've got to somehow get into frequency. Now for that, we're going to be able to use this equation, where you can see that the speed of light, c, in meters per second, equals frequency. Frequency is going to be 1 divided by seconds, also known as hertz, times our wavelength, which we're going to have in meters. Now, for the visible range, we're usually talking about nanometers, so we always have to remember to convert into meters whenever we're going to use it in the math. And if we were to look at the unitary analysis one other way, we could consider to be cycles per second. So if I draw a wave here, and this is all supposed to be a uniform wave, but my skills of art aren't awesome. And here's my x-axis. All right, so from the point where it crosses the x-axis, that's going to be one wave. That would be one cycle. So how many of these per second do we have? That's going to be frequency. How long that wave is, well, not great. There we are. That is going to be the wavelength, meters per cycle. Now to do that conversion, we're going to use the speed of light in a vacuum. Notice that here we have more sig figs listed than probably any textbook that you're looking at. 3.00 times 10 to the 8th is pretty typical. 2.998 times 10 to the 8th is pretty typical. Obviously this has 3 and 4 sig figs. But if we want, we do have the really high-end values sitting on our shelf. We know this to 9 significant figures shown, and it's an exact value, which means that it acts as if it has infinite sig figs. Whenever we round it shorter than that, of course, we start having an impact on our significant figures. However, based on what you've seen in a laboratory classroom, you're rarely going to have measurements that have more than 7 sig figs. So you're probably not going to need all 9 of them. And in fact, most of the time in the lab we're limited to 3 or 4 sig figs, which is one of the reasons that you'll often see it abbreviated as 9.00 times 10 to the 8th meters per second, or 2.998 times 10 to the 8th meters per second. Remember, if you round it, it's no longer exact, so use the sig figs that you've written. Now, if I have monochromatic light, like the kind we get from, say, a green laser pointer, what we're going to have is going to be some beam of light. And that means that really what we have are a bunch of photons. I'm going to draw them as if they're particles for the moment. And remember that inside of each of these particles we have some quantity of energy. And we could go ahead and calculate that if we wanted to. If I just tell you that a common laser that's green laser pointers, are going to emit at 532 nanometers, we could convert that into meters. We could plug that into this equation right here. We could use our speed of light right here, rearrange it, and solve for frequency. We could then plug frequency back into equals h nu, and there's the energy of a photon. We're probably going to be talking about lots of photons, so we're probably going to talk about energy per mole. That way we have a big enough piece of energy to talk about. But that's getting a little further than we are right now. So if it's monochromatic, and I put this through a prism, what I'm going to see is, I'm going to have it refract here. Oops. We're going to have one line of green laser emitting on the other side. It's just going to be refracting and bending. It's not a great picture of it, but it's good enough. We're going to see one dot on the wall. Now, if we had multiple colors here, suppose that I went ahead and grabbed a red laser as well. Let's say that that red laser happens to be going in exactly the same position as the green beam. It's going to refract just a little bit differently. We're going to see 2 different beams on the wall. We'll have 2 monochromatic lights, and if we consider them both together, they would be a polychromatic light. We're going to have multiple kinds of photons present with different wavelengths, or frequencies if you prefer to talk about frequencies. Now, the best example of that we see in everyday life is going to be a fairly white source, and that's called the sun. Now, the reason we call the sun white is that it's giving off all the colors in the visible range simultaneously. Sometimes we'll refer to white light sources that are outside the visible just remember in that context we're saying that all of the frequencies or wavelengths within a certain range are being emitted. But when we're talking about visible light, we're almost always going to be just saying white and not adding that extra notation of how big of a wavelength range we're discussing. Now, if we were to put white light through that, let me just go ahead and erase all of that. If I put white light through that, my single beam is going to spread like a rainbow. If you've got beveled glass on your bathroom mirror and you ever have light reflect off of it, or you've got beveled glass on your front door, or you just have prisms someplace in a sun catcher or something, you know that you get a nice little rainbow happening here. If you haven't, driving down the street, you've probably seen a rainbow at some point in your life. In that case, a drop of water is acting as your prism. That rainbow is going to be all the colors of light present spreading out. That said, there are a couple of missing frequencies in there, very narrow, and that's something we can bring up if we're talking about solar spectroscopy or star-based spectroscopy, but we're not going to be talking about that in this video. Now suppose that we take a wave, and you can see here I've set this up in Excel. It's handling all of the equations. I'm just hiding the math on that. You can see here that we're going to have an amplitude, and we're going to have a wavelength. If we change our wavelength longer, it's going to stretch out our wave. If we make our wavelength shorter, it's going to compact the wave. The length of the wave gets shorter. And remember that wavelength is going to be the symbol lambda. Amplitude, which you'll see occasionally, is going to be using capital A as its variable. But there's something really important here, and I've seen some textbooks, including the Tro book, that say something that's a little bit confusing. They talk about amplitude being how intense something is. A couple pages later they mention that the energy of a photon is a certain quantity. It's quantized. You've seen that word before. So a quantum of energy within that is going to have a certain amount of energy. One photon can't have a higher amplitude, can it? Because that would mean it's got more energy. So here's how I really want you to think of this. We don't want to think about photons as having amplitude. We can think of ocean waves as having amplitude, and sure enough, if those waves get taller, they've got more energy. Sound waves, if they get taller, they've got more energy too. However, for light, we're not going to be thinking in that context. For light, a single photon has a fixed amount of energy. If you want to make something brighter, you can't make the photon have a bigger wave. To make something brighter, you have to have more photons.